in this section, 13.2, we're going to talk about how we can use derivatives and the idea of the derivative being positive, then changing to negative, increasing, then decreasing, or the derivative being negative to positive, decreasing, then increasing, to find what we call relative extrema, maximums and minimums, right? Because oftentimes we might come to a problem where we want to find the maximum of something or maybe the minimum of something. Like maybe if you want to maximize your product, what's the maximum profit, or if you want to minimize your cost, you want to find either a maximum or a minimum. This first example talks about a television commercial for some sort of a soft drink, and they have given a function that talks about the person's attention span, and they want to find the maximum attention span for when the best time to present the commercial sales pitch, right, in the commercial. And so the person has a certain attention span, it increases, and then all of a sudden it decreases, they lose interest. They want to find this maximum time so that they can put their sales pitch at that perfect time in the commercial. You might notice that if we can figure out when the function is increasing and then changes to decreasing, we can find that maximum. And we did that in the last section. We used our derivative to figure out when our derivative changed from positive to negative, or negative to positive. Now, if we were finding the derivative changing from negative to positive, wouldn't that be decrease to increase? And then what would we be finding? Yeah, we'd be finding a minimum value. Well, that's kind of what we're going to talk about in this section. How can we find not only when a function is increasing or decreasing, but when we have a maximum or a minimum? So we might have local extrema, or relative extrema they're called, maximums or minimums. If you look at this example number 2, it gives us a graph, kind of has a whole bunch of humps, hills, and valleys. Some of them are smooth, some of them are pointed. And it says here to identify the x values of all points where the graph has a relative extrema, a relatively high point or a relatively low point. So it gives us a couple of different x values here. It looks like x sub 1 is a relative maximum. It's a relatively high point on the graph, where the graph goes up and then it comes back down. Or this next point, x sub 2, is a relative minimum, where it goes down and then it comes back up. So any of those kind of hills or valleys. If you look at x sub 3, it also has a relatively maximum value there. It's not necessarily a smooth one, but I can still have a maximum even at a sharp point. I can have a relative maximum at a sharp point. So you might kind of be able to make some connections here with critical numbers that we talked about in the last section. Where are all of these relative minimums and relative maximums happening? Look at x sub 4. X sub 4 is also a relative minimum. So I could have multiple relative or local extrema. Relative maximums at a couple of different places, smooth and sharp, and relative minimums at a couple of different places on the graph. So we're going to add to that idea here in a little bit and talk about where we can find those relative maximums and minimums. So it says here, if we have a bounded graph, you might have noticed on this graph that both of the endpoints are arrows. That means it's going to keep going down forever and then keep going up forever on the right side. But if I have a bounded graph where the endpoint ends, there's a solid ending point, I can say that the endpoint is also a relative maximum or minimum. Now, some books will argue that you don't know what's happening on the other side of this. The graph could go up and be a relative minimum, but what happens if the graph goes down and continues to go down? Then this point wouldn't be a relative minimum. But your book is going to say that you could have relative extrema at all of those different hills and valleys and at endpoints. So you might notice that at every single one of these hills and valleys, what is your slope? Well, your slope is either 0 or your slope is undefined at this sharp point, right? And so what is your derivative at all of those different values? Or what can you tell me about where all those relative maximums and minimums are? You might notice that all of those relative minimums and maximums are either where a derivative equals 0 or where a derivative doesn't exist, or at an endpoint. So we can hopefully find some relative extrema if we can figure out first where those critical numbers are, where your derivative equals 0 or where it doesn't exist. And then make sure though, because just because they're critical numbers doesn't mean they're relative extrema. And that's kind of what this section is saying right here. If I have a relative extrema, if you know it's a maximum or a minimum, then there has to be a critical number there, or it's an endpoint. But the converse isn't necessarily true. The reverse isn't necessarily true. Just because I have a critical number, my derivative equals 0 or doesn't exist, doesn't always mean it's going to be a maximum or minimum. Take, for example, the function x cubed. An x cubed graph kind of looks like this, right? Well, if you look really closely at x equals 0, the derivative, it increases, it goes flat for a second. The derivative is 0, and then it goes back up, right? And so the derivative, there's a critical number there at x equals 0. The derivative equals 0 right there. So there's a critical number. But that critical number is not a maximum, and it's not a minimum. It's neither, right? It increases, stops for just a second, and then it increases again. So even though it's a critical number, it is not necessarily a relative max or a relative min, so you've got to be careful. If it is a relative min, then you know it's a critical number or an endpoint. But we can narrow it down to figure out where all of those maximums and minimums are by first finding all of those critical numbers, figuring out where the derivative equals 0 or where it doesn't exist. But then what we have to do is we've got to figure out what's happening on either side, right? We're going to talk about that in the next video when we can figure out if we can tell if it's a maximum or a minimum or if it's just a critical number, kind of like an x cubed graph. So critical numbers are only possible extrema. You can't guarantee it until you give me a little more information.